So today we're going to cover section 5.4 in our textbook, which is solving special systems of linear equations. So before we jump into actual systems of equations, let's go back and remember how we saw special solutions before. So when we were working with just one variable and one equation, kind of like 3x plus 5 equals 11, when we're solving this, we're looking for the value of the variable that would make that true. So over in the margin here, if we solve that, we'd start by subtracting 5, and then we get 3x is equal to 6. So when we divide by 3, we get x equals to 2. X equals 2. What we're saying, though, is that x equals 2 is the only value that would make the original true. So if I plugged it back in, I'd plug in 2 wherever I saw an x. So 6 plus 5 is definitely equal to 11. If I tried to use any other number, like here I plugged in x equals 1. When I plug in x equals 1, I get 8, and 8 is not equal to 11. Right, so here we're just seeing that I plugged in x is equal to 1. So x equals 2 is the only number that would make that true. Now, when we are solving equations with one variable, sometimes we run into what we call special solutions. And there was 2 types of them, so we have 2 examples below just to remind us. So like with special case number 1, what we would start by doing, it would be like distributing that -2. So we have 4x minus 8 is equal to -8. So what we see here is that these 4x's cancel each other out. So I have -8 is equal to -8. Now, what that means, this statement right here is a true statement. So it's telling me no matter what I plug in for x, the equation will simplify to something that is true. So that tells you my answer is I could use any real number. So we'd say all real numbers. So again, I have some ideas prepared that what that means is I can plug in anything, or we'll say any number makes this true. Because when I simplify it, it always simplifies to a true statement. So my example that I have prepared here, if I tried 2, right? I said here that any number should work because we saw a true statement. So if I plugged in x equals 2, what I can see by simplification is that, yes, -8, so 8 minus 16, that is -8. So what works for x equals 2? But I could keep trying. Like here I have x equals 0. If I plug in 0, I do see that -2 times 4 is -8. So one of our special solutions was that any number could make it true. So there was an infinite number of solutions. Now again, that's how many there are. The actual answer to the equation is all real numbers. X could be anything. Now the other special case that we saw is over here in number 2. So we'd start by simplifying the right side. And simplifying the right side, we could distribute the half. So half of 6x is 3x, and half of 10 is 5. So when we're solving, we'd want to get the x's on the same side. So I'll start by subtracting 3 x's. And here we can see that the x's disappear. So 3x and -3x cancels, so we have 6 is equal to 5. Now this statement right here is false. So what that means is no matter what I choose for x, I'm going to plug it in and it will never make the equation true. So the actual answer then, what values of x can I use? There are no solutions because there is no x value that I can plug in that would make it true. We could also say no real numbers. I'm okay with either or. So what that means is if I choose anything, like if I chose 0, there will be nothing that I could plug in to make it true. So here I'm just showing one check of 0. So 6 is not equal to half of 10, right? So 6 is not equal to 5. So those are the 2 special cases where we either had an infinite number of solutions, which was seen by finding a true statement when we simplified, and then there was no solutions, which we saw because we get a false statement when we simplify. So there's the same type of thing when we work with systems of equations. So just like regular equations, like we started here, we could get an answer, like just one answer that makes it true. That's the same thing that we saw with systems of equations. We focused on this stuff in 5.1 to 5.3. All of those, we found a point of intersection, or we found this XY pair that when I plugged it back into the originals, it made both of them true. But just like with our special solutions for one equation, we could have no answers. So like if I was asking you where two lines touch, they could never touch, right? So we see this like they're parallel lines. Parallel lines would never intersect. So if we're looking for the point of intersection, there is no point of intersection. Just like we did with one variable, sometimes we get an infinite number of solutions. We know that from section 5.1, solving a system on a graph would be where do they touch. So here, it's good to note that there's two lines on top of each other. If I asked you where these two lines touch, well, if they're on top of each other, then they would touch everywhere, which means there's an infinite number of points. So if two lines are on top of each other, we could also just say that they're the same line. So let's go see how that looks when we're solving some. So those are our three special solutions. So the first example here, we want to solve the system of linear equations, and we can do this in any method. Now with this one, since they're both in a graphable form, I think we should use graphing. So our blue line has a y-intercept of 1 and a slope of 2. So we'll go up 2 over 1, up 2 over 1, up 2 over 1. And we'll plot as many points as we can, because if we're solving graphically, we want to make sure that we see the point of intersection. And then we'll graph the red line. The red line has a y-intercept of -5, and its slope is also up 2 over 1. So positive 2. Now what I see here is that I'm never going to touch the blue line, because we notice that these two lines are parallel. We can observe that since they have the same slope, they are parallel. And parallel lines never touch. So where do these intersect? They never do, so there are no solutions. Now that's how we can see it on a graph. That's very easy. Let's also take one other method just to see how it would look with that. Let's use substitution. I also like substitution because we have a variable that's solved, so I could take this y and plug it into the other equation. So wherever I see y, I can replace it with 2x plus 1. So in the red equation, rather than calling it y, I can call that 2x plus 1, and that should be equal to the right side, which is 2x minus 5. So what we see here is when I'm trying to get the x's on the same side, like if I'm subtracting two x's, all the x's disappear. So here I just have a positive 1. These x's disappear, and I'm left with a -5. 1 is equal to -5. That is not a true statement. That is false. So what that means, there are no solutions that would make this ever be true. Just like we saw when we were working with one variable, when we got a false statement that keyed us in that there was no numbers or no solutions that we could use to make an equation true. So in other words, we see that same thing when we're working with systems of equations. When I'm trying to solve something and I see that I get a false statement, that clues us in as there's no solutions. So here this tells us there's no solutions for x. So if I can't find an x value, then I obviously can't find a y value. Let's look at this second example. Now with this second example, when I'm solving this, they're not already in a graphable form, like I'd have to rearrange it for y equals or something, but I do notice that they're almost ready for elimination. When I look at the coefficients, they're not exactly the same, but I would be able to multiply one of the equations to get them to be the same. So with the first equation, and again, I'm just labeling them, this is my first equation, this is my second equation. If I took my first equation and multiplied everything by 2, that would help me get the same coefficients. And remember from section 5.3, our elimination, that we want either the same or opposite coefficients. So I'm just going to rewrite this line below. So if I multiply everything by 2, -2x times 2 is -4x. 2 times y is positive 2y, and then 2 times 3 is 6. So now, just like I did in the substitution method, when I notice that I have the same, the elimination method, when I notice that I have the same or opposite coefficients, I just ask myself, what would I do with -4 and -4, or what would I do with 2 and 2 to get them to be zeros? Well, I would subtract them, right? -4 minus -4 would change to a plus. So -4 plus 4, that's 0 x's then. If I had 2 y's and I subtracted 2 more y's, well then I have 0 y's. And then 6 minus 6 is 0. So we can simplify. 0 times anything is 0. 0 times anything is 0. So 0 is equal to 0. Now what we should notice with this, that is a true statement. And the reason we care about a true statement is, as we remember from our work in one variable, just on the first page of our notes here, when I saw a true statement, that means no matter what I plugged in, I'd be able to find an answer that works. So that means there was all real numbers, so an infinite number of solutions. So down here, we have the same thing. There are an infinite number of solutions. Now, we can't say any real number. We 100% cannot say that as our answer. And what we need to clarify is that it is any XY pair on the line. So let's look at that as our final method of solving this. I can't just choose any real number. Like if I choose 1, 1, 1, 1 is not guaranteed to be a solution, right? And if I can just see by plugging that into the first one, like if I took negative 2x plus y is equal to 3, and I plugged in 1, 1, I'd get negative 2 plus 1, times 1, excuse me, plus 1 is equal to 3. Well, negative 2 plus 1 is not equal to 3. So I definitely found an ordered pair that didn't work. So you cannot say any real number here. We have to say it's any real number XY pair that's actually on the line. So let's get a picture of that line here. So this here is pretty easy to get y alone. We just add 2 x's to both sides. So that is here, and it has a slope of 3. Or sorry, only a slope of 2. Y-intercept of 3 and a slope of 2. So I'm just sketching that line, and then we'll connect the dots. Now I'm going to use a highlighter just so we can see that it's lying right on top of it. But with the highlighter, I'm going to graph this red line here. And this red line, when we get it alone, I can just do in the margin here. We'd start by adding 4 x's. And then we'd have to divide everything by 2 to get y alone. So we see that we have the same equation that we just did. So if I was graphing it, I would place a dot here, so they intersect there. I'd place another dot there, another dot there. I'd place another dot there. So I'm finding all these points where I've placed a point of intersection. But when I connect the dots, that's me placing all the other points. And here I'm just placing all the other points on the other line. So I can see that they touch at an infinite number of XY pairs. But that XY pair isn't just any random combination. How do I find one? Well, I can use the equation. Give me a point that's on the line. Well, just pick an X value. So I know like at 0, 0, 3 is on the line because it's on my graph there. If I plugged in like X equals 5, let's do a little smaller value so we can see that it works. If I plugged in X equals 3, I get y equals 9, and I can see that at x equals 3, that point is on my graph. So if I ever ask you to give me a solution, you just said there was an infinite number of them. Well, give me one of them. You just find a point that's on the line. So again, today we're summarizing by looking at special systems of linear equations. So one solution is not special. That's normal. We'd expect to find a point of intersection of 2 lines. But sometimes we can find when they never have a solution, which means that the lines never touch each other. Or as we saw algebraically, that we get a false statement. Finally, 2 lines could touch everywhere if they happen to be the same line. So there's an infinite number of XY pairs. So on a graph, we see that it's the same line on top of each other. Algebraically, we see that we get a true statement.